So today we're going to start by looking at some practical considerations, practical issues when training deep neural networks. And then in the second hour I'm going to talk about convolutional neural networks. This first hour will be just a general overview of different issues and different solutions for specific problems. But basically the overall theme is what you need to think about and decide when you're starting to train your neural network. So before you start training, checking the parameters that you use, regularization, things like that. So in general, the hyperparameters that you have to decide to try to get the best results. So we'll start by looking a bit at model selection, how to choose the best network for what you're trying to do, adjusting the learning rate and some other details, weight initialization, and then we're going to look at regularization, but before that I'm going to talk a bit more on a theoretical level about this bias variance decomposition, so it's easier to understand what regularization will be doing. So first, what we need to choose to set up our network. The idea is that we need to, we have a model. The model is the expression, the abstract expression of all the possibilities that we are searching to try to find, for example, the best classifier or the best regression. And then we are going to instantiate that by training our model. So in this case, our model is a neural network. We're going to train the network. At some point, we're going to find a set of weights, and this is the hypothesis that we have, the final input. But before we reach that, we need to choose what the network is like, so the model that we're going to train. This is an example with last week's problem of trying to predict miles per gallon of fuel consumption in cars from that data set. And you can see that using this network with 150, 10, 1 neurons in the layer, so it's a dense network, like a multi-layer perceptron with this number of neurons. And you can see that we can get the training error very low, but then outside the training set, the validation error is fairly large. So this is a problem. It seems that our network is adapting too much to the training set, but then it doesn't generalize well. This is what's called overfitting, and it typically happens when we use a model that is too powerful for the data that we have. So in this case, it would be best to try a smaller network, for example, 30, 10, 1, and you can see that the training error, which I represent here in blue, increases when we go for the smaller network. So it's not as good as the other one to fit the training data. But the validation error, the error we're measuring outside the training data, decreases. So there is less of a problem of overfitting. This is one of the things you can do. We're going to see that we can also use a model that is overfitting and try to improve things with regularization. But basically, if you get a training error that is not good, a high training error, then you know that your model is not even able to learn the training data. So that would be a bad model. If you have a model that trains too much on the training data and then the error on the validation set is high, then one of the options is to use a simpler model and try to get the best results by adjusting the complexity of your model. So the first step would be what kind of model you're going to use before even you start training. So you can try out a few of them just to see what happens. Then we need to initialize weight. So this is a fairly simple issue because we mostly don't understand how this affects the network. So there is no theoretical foundation other than a very basic principle that if you start with the neuron weight all the same for all the neurons, then since you have if you have a deterministic optimization algorithm, it will always do the same thing for all the neurons, so you actually don't learn anything. Even if you have something that is non-deterministic, as we'll see later with dropouts or things like that, still you start with all the neurons in the same way, and it makes it very hard for the network to learn anything good. So The basic principle here in weight initialization in neural networks is that you break the symmetry and you make all the neurons different from each other at the beginning, so that the network can find a path to optimize things. Basically, you need to do this with the weights. The bias values you can start at 0, because we can think of the weights as the weights are those values that are multiplied by the input to the neuron. But the bias values are multiplied by 1 or just added, so they simply shift the place the function is firing. So it's not as critical to have to initialize those. We can just start them at 0 and let then the network find out, as long as the symmetry is broken on the actual weight. There are some more sophisticated ways of trying to initialize other than the default, which is basically using a Gaussian distribution or a uniform distribution between -1 and 1. The idea is that you don't start with weights very large, you start with small weights so that you don't saturate the output or don't get gradients that are too steep. But you can improve this a bit in some cases. So one idea is to choose the initial weight as a function of the number of inputs into that layer. So this would be a uniform distribution between 1 over the square root of the number of inputs minus that and plus that. So between around 0 inside that interval. Or you can actually take into account not only the number of neurons, but also the number of inputs, but also the number of neurons. So M is the number of inputs into the layer and the number of neurons into the layer. There are some reasons to suspect why this would be better to scale the initialization or closer to 0 the larger the network is. Although in practice sometimes this works, sometimes they don't. Usually just the Gaussian initialization works fine. The important thing is that you really need to randomize the weights, otherwise they all start the same and then the network cannot learn. One thing that we do always when we're training a neural network, and in general for machine learning, is to rescale our inputs so they are approximately close to 0. This sometimes has a good reason. For example, if you have features like years and kilograms and cubic meters or things like that, you need to find a common scale for all the features, otherwise the difference in magnitude will not make sense anyway. For neural networks, there is the additional problem that if you start with values that are too large, you make it harder to properly fine-tune the neurons to work with those. So we use standardization typically for inputting the values into the network, which these terms may be misleading because standardization usually refers in machine learning to subtracting the mean and dividing by the standard deviation. So you reduce the distribution to 1 with the 0 mean and the 1 and the standard deviation of 1. Normalization refers to rescaling everything to be, for example, between 0 and 1. Here, in batch normalization, it's actually a standardization that is being performed on different layers of the network. The idea here is that you can imagine that part of a network, of a neural network, is just one neural network that receives as input what the first part output, so the activations of the first part. So this part of the neural network would also benefit from having standardized inputs exactly for the same reasons as the initial part, as the input layer does. So we can add this standardization, which is called batch normalization, it's actually standardization, that computes the mean and the standard deviation for each batch of examples, or keeps a running mean and standard deviation from the previous batches, and then standardizes the output of one layer so that when it's fed into the next layer, it comes in this distribution close to 0 and standard deviation of 1. This not only makes it easier for the next layer to learn, but it also reduces the effect of the previous layer changing where the data is being represented. So if you imagine the network training, all the weights are changing, and one layer is trying to learn how to properly represent the input values it is receiving from the previous layer. But at the same time, the previous layer is changing the way it presents the values to that next layer, because it's also learning different representations. And these may be, we may think of these as two types of changes. Some of them are useful because they are separating the data properly. We saw in the first lectures those transformations. Okay? Some of them are not very useful because they may just be shifting the data from one side to the other, or just spreading things out more or less, but without actually changing the shape. And the next layer not only needs to adjust to the change in the shape of the values that it's receiving, but also to all these changes in the mean and the variation of that data. When we use batch normalization, we remove those changes, so that each layer can focus only on the shape of the data and doesn't need to relearn where the data is centered and how much it's spread out. So batch normalization is something you can include in your network. For example, in Keras you can include layers of batch normalization, and it tends to improve a lot the learning of the network. Another thing we need to fine-tune is the learning rate for the optimizer. Of course, there are other parameters depending on the optimizer, things like momentum and stuff like that. So depending on the optimizer, you may have to fine-tune several parameters, but learning rate is something that is general for all of them. You'll find this, and it serves as an example of how you can try to adjust these parameters. So one problem with learning rate is that if you have a too small learning rate, it will take too long to train the network, and you may fail to converge to the right solution even. But if you have a learning rate that is too high, the learning rate determines the size of the steps the optimizer is doing when it's trying to minimize the loss function. And if you give too large steps, you may fail to find the optimal point. So you may jump around the point or to the other side and then fail to converge. And you can see this if you plot the error over for example, different epochs. You can see this oscillation in the training error. Seeing some oscillation in the validation error is expected in many cases, because the validation set is not the same as the training set. So an improvement in classifying the training set, for example, may lead to becoming worse in the validation set. So it's often the case that you can see some fluctuation in the validation error. But it's not expected that you'll see much fluctuation in the training error, because this one should be minimizing steadily. If it's not, then it means that you're jumping too much, so you're reaching a place that is higher in the loss function instead of lower, and this is an indication that your learning rate is too high. So if you reduce the learning rate in this case, what you can see first is note the steepness of this descent. So if the learning rate is lower, it takes longer to reach the same error rate. But now it's more stable, so you can reach, in the end, you can stabilize and converge to a better solution. So the idea roughly is to try to put your learning rate as high as you can, while not causing any convergence problems here. Why not becoming unstable at the end? So that way you make it as fast as possible in training, but don't lose the ability to converge to the right solution. Okay, so now we saw when selecting models this problem of having models that are too powerful and adjust too much to the training data and then don't generalize well, or models that are that don't have power enough to adjust to the training data, and so you cannot even lower the training error in that case. But these are different problems that we can solve in different ways. So to understand that, let's try to decompose the error into these two components. So statistically, a bias is an average error in some estimator. So if you're trying to do an estimate and on average your row is missing by some amount, that will be the bias of your estimator. So the bias of a model here means that we are trying to predict some value, but on average we are missing by some factor always to the same side. So on average this will be the difference between our prediction and the true value. But what does it mean to say that the model on average misses that prediction? If we train the model on one data set, then we have one single hypothesis, and this is not an average, this is just one error. So what we need to imagine here is what would happen if we could train the model over different samples of the data. So suppose you gather one training set of 1,000 examples, you train your model, you have one hypothesis, but now you do that again. You buy a new data set and do it again and again and again, and then you check what are your predictions for a specific example, one that is outside all of those training sets. And if that prediction is biased, that is, you're always overestimating or underestimating, that's a measure of the bias of your model. So imagine we did that. This would be the point we're trying to predict, for example, and these would be many data sets that we had collected. We always use the same model, we minimize it, and these are the predictions we get from different hypotheses we obtain when we train the model in different data sets. In practice, you can do this by bootstrapping if you want to do these kind of things, but for neural networks it doesn't make sense. This is more a theoretically conceptual analysis here. But what can we say in this case is that our model does not seem able to fit the data properly. So the points are spread like this, but our model is too stiff to adjust to that curve. So over here, it will tend to overestimate the predictions. So it's predicting the values here while the true values fall down here. And in this size, around 2, it does the opposite. So it tends to underestimate when it predicts things. So when we add all these errors, all these average errors when training our model over many data sets, we get a large bias, which gives us a measure of how the model is unable to adjust to the data. So all these things that are biased, that are not merely random neutral errors. So if we do this for one particular point, we see that on average our model is predicting values here, and this average error will be the bias for that particular point. If we do that over all the points, the average over all the points, this is the bias we can attribute to our model. Now another thing is variance. Variance is the dispersion in the predictions when we train our model over different data sets. So let's consider the same thing again, but now we have a different model, one that adjusts too much in this example. And for each subset of the data that we use, we get a different hypothesis that varies widely in predictions from one hypothesis to the other. So when we look at some specific point and we consider all the different instances of our model we obtained training in these different sets, we find that there's a lot of dispersion in the predictions for our points. The variance here, this is when we average over all the points, will be a measure of the variance of our model. Now the reason to think about it this way is because there is a trade-off between these two. So if we have a model that is too stiff, for example this one, it will have a large bias, but because it is stiff it will have a smaller variance, because it will tend to make the same predictions in the same place. If you have a model that is very flexible, that adjusts too much to the data, then it will have a low bias. If you average these out, these tend to fall nicely into the curve. But for each point, it can vary widely in the prediction depending on what data you use to train the model. And this is basically a trade-off where if the model is too stiff, you have a total error in the end, because the error of the model will be because of these two things. On one hand, its ability to fit the data, and the other, how much the predictions vary and do not generalize from one data set to the other. So if the model is too steep, you have a high error. If the model is too flexible, you have a high error. But here, somewhere in between, is the optimal compromise between the two different aspects, flexibility and stiffness, and where you can minimize the error. And one reason for separating these two is because if you have a model with a high bias, you can spot this because your training error will also be high. You cannot fit even the training data, the model is too stiff. And in this case, the only solution is to use another model, because if you cannot even fit the training data, then it will not work outside the training data either. But if your model adjusts too much, this means it has a high variance. There are ways of trying to prevent it from adjusting so much without actually having to change the model. So if we find some way of trading off that variance for a smaller amount of bias and improving those results, we can use a model that fits too much, but with some correction it works better than, for example, using a simpler model. And this is what we try to do with regularization. So basically, regularization is any technique that you use that changes the way the model is trained in order to try to reduce variance, to try to reduce overfitting, so that it will perform better outside the training set. Note that this doesn't work if your model is too stiff and has a high bias and low variance, because if you try to reduce variance even more, it will not solve your problem. So first you have to make sure that at least the training data your model can classify correctly. If it cannot, then you need to choose another model. But now if your model can classify the training set correctly, works well on the training set, but is overfitting, now you can use changes in the way it's trained to try to reduce that overfitting. So basically, we're going to try to throw away as much as the variance as we can without increasing too much the bias. So one thing we can do is to put a penalty in our loss function on the size of the parameters that we're using in our network. So the idea here is that if we have coefficients that are too high, we can make things curve too much. So basically we are in that, if we were looking at it in 2 dimensions, we would see those curves oscillating a lot. But if we force it to become stiffer, all the coefficients become smaller, then we reduce part of that variance. And if we do this in a way that does not compromise the ability of the model to fit the data, then we can easily find that sweet spot where the error is minimized. So this is basically what we have. We have a loss function here. We talked about those last week, the different loss functions depending on what kind of classification you're trying to do, but basically it's generally maximum likelihood, and we convert that depending on the kind of output of our network. So this is a function of the parameters of our network, the input features, and the class labels that we have. But we modify the loss function by adding a function, some function of the parameters of our network. So this does not depend on the inputs, it's just trying to penalize some function of the parameters. And this alpha here is the regularization coefficient, the weight of the regularization in our loss function. So the larger the alpha, the more we are going to try to stiffen our models in this way. Usually, this is a general expression for regularization in machine learning, where we just use a function of all the parameters. In general, in neural networks, we don't include the bias values there, because the bias values don't make our network more flexible, they just adjust where the neurons fire. It's the weights that are important to the variance. So usually in neural networks, the parameters that go into the regularization there are just the weights of the neurons. And these are two of the most common regularizations of this kind. So regularization by penalizing the size of the parameters. L2 is called ridge regression 2, is penalizing the square of the modulus of the vector. So imagine that you take all your parameters as a vector. This vector has a length. The square of that length is what is being penalized. So L2 regularization is trying to shrink the total vector of the parameter. L1 is trying to penalize the sum of the absolute value of all the parameters. This gives a different result because instead of trying to reduce the size of the whole vector, we are trying to shrink some of the parameters to 0. So what this results in is a network where some weights are 0. They are effectively turned off by this regularization, which simplifies the network a bit. L2 regularization is also known as weight decay, so this is one way of implementing it. If we consider this function to be the square of the norm of the vector of parameters, when we compute the gradient as a function of one of the parameters, as the weight, then the gradient just becomes, the 2 on the part of the square comes down to multiply, and the gradient just becomes the weight. So when we go down the gradient, the negative of that value there, it means that the update rule for the weight, that weight of the neuron, is what it was before, minus a step along the descent of the gradient, minus a constant value multiplied by what the weight was before. So this means that we are decaying the weight. At every update, we are removing a fraction of the value the weight had before, so it's slowly tending towards 0 if it's not useful for anything else. If it is, then the gradient of the cost function there will pull it back to the value it should have. If the weight is not relevant, then it will tend slowly towards lower values. But note that this is asymptotically to 0. It will not necessarily reach 0 because the smaller it is, the smaller the fraction we are shaving at every iteration. So this is called weight decay. It's equivalent to L2 regularization, except for a small detail, because this square in the derivative becomes a 2 multiplying the value here. So actually, the weight of the regularization you use for L2 regularization, if you apply it in this way, is half the weight that it would be if you were to apply it in the weight decay. So remember that multiplication by 2, because if you are using one implementation that implements the algorithm in one way and then you pass it to another, you have to adjust the constant there, otherwise you'll get different results. It will not be the same thing. But other than that, they're equivalent. L1 regularization, when you do the same thing for the gradient, it will penalize a constant value, just the sign if the weight is positive or negative, because we are using that absolute value there in the penalization. So what this does is, instead of trying to reduce the weight asymptotically to 0, so it shrinks but it will never reach 0, it can actually make the weight go down to 0, because it's a constant that we are shaving away at each iteration. So basically, while L2 regularization minimizes the total size of the weight vector, L1 makes its part, makes some weight come down to 0, so your weight vector will now have many zeros there, as many as it can do without increasing too much the loss function. Another way of doing regularization is by data augmentation. So the general idea is intuitively that the more data you have on the training set, the smaller your problem with overfitting, because you just add more data and it's easier to generalize to outside that data. Often the size of the data set that we can use is a hard constraint that is imposed by the resources that we have. But in some cases we can increase that size. For example, if you are doing facial recognition, you can reorient the faces, adjust the image, adjust the color or the brightness of the image, or mirror the faces and things like that. So you can take one image and produce many of them and increase the number of images you're using for training. You have to take care, because if you're doing, for example, optical character recognition, you cannot mirror the letters, because some of them will change, will no longer be letters and so on. But depending on the context, you can use this to augment your data set and reduce problems with overfitting. Note again that we are reducing problems with overfitting with the ability to generalize outside the training set, but this will not reduce problems if the bias is too much, if you're underfitting. So if the model is underfitting, you just throw away your model and use another one. Another way of doing this, of effectively doing the same as that data augmentation, is by injecting noise into the network. So this can be done in the input. We add a small fraction of noise every time we present an example. So all the examples will be slightly different. Every time we present an example, it will be slightly different from the time before. This coerces the network into finding sets of parameters where it's more robust and not as sensitive as, or to small variations in the input. And this is what we want to avoid overfitting, not making the network overly sensitive to those inputs. We can also apply noise to the weights of the network, or even to the output. Sometimes, because the labels may not be entirely correct, so we add a random factor to the labels while training the network, so it can generalize a bit better and not trust too much the labels that we are feeding into it, or just to do the equivalent of label smoothing. For example, consider a problem of multi-class classification. You have a softmax activation, so this means that the sum of the activations at the end will be 1, and each activation will be between 0 and 1, and gives you the probability of being in some class. If we use a one-hot encoding of zeros and ones, we are trying to force the network to give exactly 1 in one of the outputs and exactly 0 on the other. But this is only possible asymptotically on the softmax activation when the coefficients tend to infinity, because it cannot be exactly 1 or exactly 0. And so if we do that, we are forcing the network to go to very high weights to be able to approximate what we're demanding. So we can use a small margin here of tolerance, this epsilon, where the top class, instead of being, say, 1, could be 0.9, for example, and the others will be the 0.1 divided by the remaining classes. So we don't force it to be exactly 0 or exactly 1, and this allows the weights of the network to fall into more reasonable ranges and can help reduce overfitting. Another technique we can use in neural networks that is generally not available to other types of learners is this early stopping. Since we are training the network iteratively, presenting different batches and measuring the errors, this is a case, well, this is actually a bad case of overfitting too, but we can see that even though the training error keeps decreasing, the validation error decreases and then starts increasing. So it's not a good idea to train beyond this point here, because we are overfitting the data. One way of imagining this is that early stopping constrains how far from the initial values close to 0 the optimizer can take the vector of parameters. So if we stop early, it cannot go too far from 0, and the parameters will be boxed in that volume. If we keep training, then it can walk away from that and explore more that space. So this is a way of also of constraining the parameters, but we can follow the cross-validation error or validation error and then decide when to stop. This is usually done by, because training the network takes quite a while, we're saving checkpoints, we're saving the parameters at regular intervals during training, and then we look at the results and we pick the one that is closest to the optimal one. Another way of trying to minimize variance is this bagging. This is a general technique in machine learning, which is, the name comes from bootstrap aggregating, but basically what we're doing is, bootstrapping is a resampling method where we resample from our data set randomly to obtain different training sets. Then we train the models in the different training sets, so the different hypotheses will give us these curves, But now, if we want to reduce the variance without increasing bias too much, we can just average all of these predictions, and we have something that where the variance is reduced, but the bias is not increased. This is possible in theory to use with neural networks. So you could train 100 neural networks using resampling of your training set, and then average the outputs of the 100 networks when you're using them to classify. The problem with that is neural networks are expensive to train and also expensive to use. So you have to store 100 neural networks, and then you have to apply 100 neural networks to some sample to try to classify and average that, and that is not feasible. It has been done with around 10 or 15, things like that, but you cannot really do it too much. But there is one way of doing this, which is with dropouts. We are going to do this implicitly on the same neural network. Dropout seems a strange regularization method, but the idea is that for each batch we are presenting the network, we're going to drop out to inactivate neurons. Usually, in the input layer, we do this with a smaller probability, for example, 20% probability at each batch to disconnect the neuron. In the hidden layer, we can use a higher value, for example, 50%. In the output layer, we don't drop anything because then we need those for classification for the output. So basically, at each mini batch, the neurons that are dropped are simply ignored, both the neurons and their weights, and we are pretending they don't exist in the network. So each time we present a batch of examples for training, we are training with a different sub-network from the complete network. This, we can think of this as training an ensemble of networks that are provided by the different combinations that we can have of switching on and off these neurons. And so we're actually training a large set of networks in the same network and then averaging all the results, which is similar to what we do in bagging, but we do it all in the same network. Then at the end, we need to compensate for this. So there is one way of doing this is that since during training, if a neuron has been dropped 50% of the time, then when we use it to test, when you use it to classify some new examples, we need to divide its activation by 2 or divide the weights of the next neurons by 2 so that we compensate, because now it's firing all the time and we keep the same expected value. So this was the original idea. We train, we drop out, and then we rescale either the weight of the neurons in front or the activation of the neuron in order to compensate the difference. As it's currently implemented, it says the inverted dropout, which is to, during training, one of the neurons, if a neuron is dropped 50% of the time, then when it is not dropped, all its activation is multiplied by 2. This means that the network will learn the proper weight for the neuron as it behaves on average when it's active with its original activation. So this is how it's done in TensorFlow, for example. So if you use dropout in TensorFlow, all you need to do is to disconnect it when you're using the network for testing. So for example, you could use something like this. You have this placeholder which is a Boolean placeholder to determine if your network is training. You can use this placeholder with default object, which is a placeholder that has a default object. If you don't put it in the feed dictionary, it already has that object. If you put some other value, then it will replace it. And when you create a dropout layer, you can set the flag is training or not, and this will determine whether the dropout layer is used or ignored. If you, we are not going to do this like this, so you're going to use dropouts, but now we're going to use Keras because it's more practical for doing this. And Keras has, the model has a method for fitting and for predicting, and automatically disables dropouts when you're predicting. But this dropout implementation is inverted dropout. So the weights are scaled in order that when the neuron is firing, it has a higher activation to compensate for when it's dropped out. and that way the weights of the network will go into the right value. Also, L2 and L1 penalties or regularization. L2 can be actually added to the loss function because it's easier to compute the derivative. L1 is available in some optimizers. You can set it there. Another way of doing regularization is called adversarial training, and this depends on the actual example that you're trying to, the actual problem that you're trying to solve. So it may not be applicable in all cases. But the problem is that if we have an example that is classified and the weights are such that the gradient of the loss function is very steep at that point, then a small change can greatly shift the way the loss function is, so what the error would be. But since we're training with just those examples, the network doesn't find out about this. If we do this, so basically what we do here is we present this image to the network, then we compute the gradient of the loss function at that example, and we add this with a very small scale, so 0.007 in this case, and we add this to the image. And when we look at the image, it seems the same. If you look at the actual image, you can tell a very small difference, but this is a panda, this is a panda, so this is being added as a very small fraction. But since this is the gradient of the loss function given those weights of the neural network, this is enough to deceive the network, and now the network thinks this is a given instead of a panda and gives a very high confidence because we forced it to shift the classification in this way. So if we can find these examples, we can augment the data set or include in the data these examples designed to force the network into committing errors, and this will let the network converge into combinations of weights where the loss function does not have a steep gradient, where things are stable, and now it will no longer fall into these errors. So basically, we are doing the augmentation of the data set, but specifically focus on what is deceiving the network the most. And that will force the network to learn to not be deceived by this case. So basically, it forces to seek optimal values where the loss function is more stable in that region. Okay, so now we have, as you can see, we have many different ways of fine-tuning the network. We need to decide how many neurons to use, what regularization to use, what coefficients to have on the regularization, how much it will weigh, and so on. So you can have a problem where you have all these meta-parameters, so basically these hyperparameters. Hyperparameters are those that the network is not learning, but you need to decide when you start training. And there are a few strategies for doing this. If you have a good starting point and some feeling for what works best in that particular problem, one way is just to do manual optimization, where you fine-tune things a bit, look at the validation error, and try to optimize like that. But this is generally restricted to those instances where you really know what to move, what to change in order to improve the results. One common way of trying to optimize the hyperparameters is to do a grid search. So we have some reasonable boundaries for each value, for the different, say, optimizers, and different values for regularization, and different numbers of neurons in each layer, or something like that. And now we test all the combinations for those at fixed steps. This works well if you have a small number of combinations. If you have too many, then you cannot do an exhaustive search, and so grid search does not perform very well. Curiously, random search tends to perform better than grid search. You just generate combinations at random, test them, and then pick the best one. Random search has also an advantage that is easy to parallelize. You can just put different machines trying different combinations, as many as you want. A more sophisticated method, things like these Bayesian search methods, use previous results to try to build a statistical model from where it can predict what would be the result if we use some new combination. So based on the distribution of, say, your cross-validation error as a function of the different hyperparameters, you can try to predict what would be the cross-validation error if you change that parameter, and then this helps guide the search for improved parameters. This has one of the drawbacks is that it's not so easy to parallelize because you need to gather all that information to guide the next search, but it can give better results. We're not going to go into detail here. This is just to give you an idea that when you're really solving a hard problem, you can have lots of combinations here, and you need a strategy to try to optimize all these hyperparameters. So to sum up this part, we saw the problem of selecting the right model. So basic idea, if your model cannot fit the training data, just throw it away and find a new one, because that's hopeless, you cannot fix that. If your model is overfitting, then you have other possibilities with regularization and so on. Then we saw different things that we need to do, like normalizing the data or standardizing the data you get into the network, but you can apply that also inside the network. And we saw this regularization as a way of reducing variance without trading off too much for bias. So this works if you have a model that is overfitting. So the general approach would be have a model that is slightly overfitting, so you make sure it can fit the training data, then use regularization to try to fix things a bit until you reach the optimal result. Regularization, there are lots of different ways, but basically you're changing the way the model is training. You're not selecting a new model, you're just fiddling with the training to try to reduce variance. And then the strategies for hyperparameters. I recommend that you read these chapters and sections of the book, and also there is this blog post here. It's nice because it has lots of images for showing what regularization is doing, and so for getting some intuitive feeling about this, this one is a nice resource.